Hello and welcome to my presentation. I am Bahar Asgari from Georgia Tech. Let's for a moment imagine that the pandemic is over and we are in Seoul, South Korea for HPCA. I'm not sure about you, but I've never been there before, so I want to visit so many places there. I'd like to go to Seoul Tower that gives a nice view of the city. I'd love to see the Bokjeonhan Oak, an area in which traditional houses are well preserved, therefore I can learn about Korean traditional culture. We can also go to Gyeongbokgung, the largest of Seoul's 5 grand palaces, and also Bongwonsa, a temple in Gangnam area. And perhaps we can go to restaurants in Itaewon and Honghae. But maybe you are thinking that with the tight schedule of the conference, how possibly we can visit these many places that are far away from each other during our short visit? Well, you are right. Visiting all these places that are not near each other would take a long time and our energy as well. This challenge reminds me of a sparsity in recommendation systems that I'm going to talk about today. In recommendation systems that, for instance, we use to find movies, instead of all locations in a city, we have several data saved in memory. For instance, the information for all users and all the features of all movies. And then, instead of the tourist attractions that we wanted to visit, we have the information of a particular user that we need to access and process to suggest her what to watch next. Recommendation systems are broadly used throughout industry for suggesting music, movies, books, hotels, and what we can learn online. And perhaps in the future they can also be useful in healthcare, for instance, to quickly and accurately suggest medicines. Today, I'll talk about the sparsity in recommendation systems. I'll go over the most recent studies that have been proposed for quickly running recommendation systems and overview the challenges they encounter because of sparsity. Then I introduce our solution, Fafnir, that handles sparsity in recommendation systems. And I'll show why and how much Fafnir performs faster and more efficiently compared to prior work. To see what is sparse in recommendation systems, let's first take a look on their main components. Typically, recommendation systems consist of two parts. The first part is embedding tables, that are sets of embedding vectors containing users and contents features. Embedding tables are dense data structures, accessing to which is sparse. V1 to V6 are some random embedding vectors we use in our example throughout this presentation. We randomly color them in blue and yellow to distinguish them when we apply an operation on them. Since embedding tables are often large, they must be split over units of memory, for instance, ranks. To process a query, for instance, to suggest a music to a user, the first step that the recommender does is to read a few embedding vectors and apply a reduction operation on them, which is usually as simple as a summation that results in a single output vector. And of course, several of such queries must be processed. The outcome of these reductions are then processed by the second part of the recommendation systems, which are the neural networks. To utilize data parallelism, different copies of the same neural network can be mapped to different computation units. Today, I am focusing on sparse accesses to embedding tables, which create a significant portion of the total execution time in today's recommendation systems. To deliver data from any units of a memory to the processing cores, to perform reductions and then process the results using neural networks, huge amount of data needs to move from memory to the cores. To solve the main challenge of data movement, near-memory processing approaches have been proposed. They suggest moving some computing units to near memory to apply reduction on embedding vectors where data resides, and then only transfer the outcome vectors to decrease data movement. For instance, TensorDim has proposed putting some simple reduction units in DIMMs. TensorDim breaks down the embedding vectors and distributes them across memory units. Therefore, each NMP applies reduction on a part of the embedding vectors and sends a partial vector to the target core. This way, the amount of data movement between memory units and the cores is reduced because instead of sending the entire embedding vectors, only the resulting vectors are transferred. This approach, however, creates another important challenge. Since each NMP reads only a fraction of different embedding vectors that are not necessarily co-located in the memory, TensorDim cannot utilize row buffer locality. To solve this challenge, another recent NMP approach suggests distributing different embedding vectors in different memory units. Although this approach better utilizes row buffer locality, it creates another challenge. Now that the different embedding vectors required for a single reduction operation are not necessarily co-located in a memory unit, we cannot guarantee performing all reduction operations near memory. For instance, in our example, among all the required summations, only the sum of V5 and V6 can be done near memory because they are in the same memory unit. Other NMPs, however, cannot perform reduction operations because they don't have access to all their required operands. Therefore, they all need to send the vectors to the cores, which results in the same amount of data movement. So we cannot process embedding vectors where they reside because they are not co-located in memory, and we do not want to process embedding vectors in the processing cores because it causes huge amount of data movement. Therefore, we must process embedding vectors while we gather them from any random location of memory. So let's see how we can do that. To see how we process embedding vectors while we gather them from any random memory units, let's go back to our example and consider for a second that we don't have any NMP units or any connections. For query 1, we want to sum V1, V2, V5, and V6. What if we have two dedicated processing elements or PEs, one to sum V1 and V2, and another to sum V5 and V6? Then we would need one last PE to sum the two results. Now that we have these three PEs, we can connect them in a tree and use them to also perform the other query. In these two examples, all PEs were always performing reduction. What if we need to apply reduction on V1 and V6? Well, in that case, the first two PEs can simply forward the inputs to the next level where they can get reduced. This tree that connects all the memory units in a memory system is our proposed efficient near-memory reduction tree, or Fafnir. Each node of Fafnir simply decides whether to reduce or to forward. Therefore, sooner or later, the corresponding embedding vectors meet within the tree and get reduced. The other question to ask here is that how to optimize the number of accesses to memory. As we see here, some embedding vectors are used in a few subsequent queries, and in fact, such patterns occur quite often in recommendation systems. One way to benefit from such patterns is to cache data, as used in prior work. However, caching mechanisms are not very efficient. Therefore, instead of caching, Fafnir uses a simple mechanism as I explained in the following. Instead of processing queries as individual sets of vectors that we need to access, Fafnir processes a batch of queries as a single set of vectors that need to be accessed. And for each vector index, we have a set of queries to which a vector belongs to. This way, Fafnir reads all the unique vectors in a batch only once, and then each PE decides what to do with the vectors depending on their lists of query. In this example, the top PE uses V1 twice and adds it to both V2 and V3, and the PE in the bottom uses V5 twice and adds it to both V6 and V4. Then the root PE performs the final summations. In other words, Fafnir takes advantage of embedding vector locality across multiple queries, and that locality is exploited in the PE buffers through streaming operations. As a result, as we saw, in the end, not only do we fully utilize our tree to simultaneously process all the queries in a batch, but also we didn't need any caching mechanisms. A beauty of Fafnir is that we can also use it for running other applications, because the tree we have here is also a key reduction operation that is required in other applications, such as in sparse matrix vector multiplication. There are of course differences. For instance, in SPMV, data is sparse, not a pattern of accesses. Therefore, in SPMV, we always read from all units of memory, and PEs don't need to decide what to do. They always apply reduction. Besides, for SPMV, the leaf PEs need to first apply multiplication on the inputs. For details about using Fafnir for SPMV, please refer to our paper. To implement the mechanism of deciding whether to reduce or forward, each PE in Fafnir includes a few compute units that simply compare the inputs. If the two inputs are related, we reduce them and send the outcome to the next level of the tree. If not, we simply forward the input to the next level. Each PE also includes input FIFO buffers for pipelining. Fafnir can be integrated with various memory systems. In our current implementation, we connect a total of 32 ranks using 31 PEs. Therefore, one leaf PE is connected to 2 ranks. We break down the tree and implement it in 2 sizes of chips. The dim rank chips, each of which includes 7 PEs, and connect 4 DIMMs together, and only 1 channel chip including 3 PEs. The outputs of 4 dim rank chips are the inputs to the channel chip. Alternatively, the leaves of the Fafnir could be connected to the pseudo channels of an HBM or high bandwidth memory. We evaluate Fafnir based on a Xilinx FPGA and ASIC design at 7 nanometer. Our toolchain for these implementations is shown in this slide. We evaluate Fafnir for 2 applications: recommendation systems, for which we use DLRM and DCM models, and our datasets are Kaggle and Terabyte, and SPMV on the sparse matrices from pseudo-sparse dataset. Our baselines are TensorDIMM and RecNMP for evaluating recommendation systems. For the performance of SPMV, we compare with the 2-step approach the state-of-the-art implementation of SPMV. Let's first compare the single query latency of Fafnir with baselines. The computation time of TensorDIMM, which pipelines the processing of the vectors, is about 2.5 times slower than Fafnir, which processes all vectors in parallel. Although the parallelism level of RecNMP is similar to that of Fafnir, its computation time is not as low as Fafnir, because RecNMP forwards a few, here about 25%, of computations to the CPUs as a result of lack of spatial locality. In terms of memory, Fafnir and RecNMP are identical, since they similarly utilize rank-level parallelism and row buffer locality. In this example, the memory time of TensorDim is about 4 times slower than RecNMP and Fafnir, which could have been up to 16 times slower in the case of no row buffer hit. To evaluate the impact of accelerating the embedding lookup on the overall inference time, the diagrams in this slide show the end-to-end speedup of a prior work, RecNMP in the left and Fafnir in the right, over the baseline of a one-rank memory system when increasing number of ranks from 2 to 32. The inference time is broken down into 3 parts: embedding lookup that Fafnir optimizes, fully connected layers or FC, and other processes that are not the focus of this paper and assume that do not change when the number of ranks increases. While for fewer ranks, both RecNMP and Fafnir work close to the ideal linear speedup shown in red line, Fafnir keeps following the red line more closely as the number of ranks increases to up to 32. This stems from the key difference between RecNMP and Fafnir, which is the ability to perform all reductions at NMP without relying on a spatial locality. Next, we evaluate scalability. In a scalable design, increasing the batch size must help increasing the throughput. To evaluate scalability, the diagrams in this slide illustrate the speedup over RecNMP when batch size varies. As the diagrams show, the speedup of Fafnir over RecNMP grows with the batch size. In other words, while for the batch size of 8, Fafnir works about 3 times more quickly than RecNMP, for batch size of 32, Fafnir works about 12 times more quickly than RecNMP. In addition, as the striped part of the figures show, Fafnir achieves up to an extra 3 times the speedup by more efficiently eliminating redundant accesses to memory without using caches. For RecNMP, we assume a 128 kilobyte rank caches that offer the optimal hit rate of 50%. Our proposed chips at about 6 milliwatts per DIMM, which is about 24 milliwatts per 4 DIMMs, and in total about 100 milliwatts for a 4-channel memory system, which is negligible compared to the 13 watts power consumed by each DDR4 DIMMs. The diagram in the left shows the power distribution of a PE for our ASIC design. As shown, power consumption has a uniform distribution, which prevents the creation of a hotspot. In addition, our FPGA implementation working at 200 MHz consumes about 0.2 watts per DIMM rank node and 0.18 watts per channel node. The breakdown of the dynamic power consumption of our FPGA implementation is shown in the diagram in the right. Today, I introduce Fafnir, an intelligent reduction tree that, while gathers data from random locations of memory, also processes them. We have seen that Fafnir does not rely on spatial locality and therefore minimizes data movement. We also saw that Fafnir fully utilizes row buffer locality. Besides, since Fafnir uses a tree structure, it uses fewer connections compared to an alt-wall connection. Fafnir eliminates extra accesses to memory without using any caches. And last but not least, a beauty of Fafnir is that it can run SPMV, a widely used sparse kernel used in several applications. Thanks for watching. I would be glad to answer to any questions that you might have during session 10B on Wednesday, March 3rd at 12:30 Eastern Time.